Our second lecture, we're going to be talking about the method of joints, which is an analysis technique for determining the internal response of structural members to external loads. This picture, let me turn it over here just a second. I gotta put this on the podium PC. This is a picture from Michigan. This is called the Mackinac Bridge, and the Mackinac Bridge connects the upper peninsula of Michigan, which is right here, to the lower peninsula of Michigan, which is right here. And it goes across this this place where there's no land, goes across Lake Michigan and Lake Huron, and is the third longest suspension bridge in the world. I took this picture from the south, and I took it from a far away because I wanted you to see the lead-in and then the center span. And you'll notice that on the center span, it's extremely arched, and this view just really showed that arch nicely. You also see these big towers, and from the towers are a bunch of cables that actually suspend the bridge. So the cables, I wonder if I can get a better picture. Hang on, I'm just going to get a general suspension bridge. The cables actually are in tension because they literally suspend the bridge. But so here's just a picture, first one that came up, not a particularly super picture, but a suspension bridge. You can see that basically this one is arched, and that we have cables hanging down. Everything is suspended from these towers. So the center span is really, to me, the most interesting part, because the side spans reach land, and you can see that there's a buildup here in order to support the weight, and a pylon here to support the weight. Same thing over here on the other side. But the center is all suspended from these cables, and all of the tension in the cables is transferred to compression in the center span and compression in the towers. So it's just kind of a cool thing. There's another on your course homepage. There is another bridge. This is just a simple truss bridge, and these are all around. You may have seen these are railroad trestles. This type of a bridge is called a Warren truss. There are other shapes of trusses, but trusses are always built on the shape of triangles for reasons that we're going to talk about a little bit later today. But once again, this is not a suspension bridge. Some of these are called structural members. Some of these structural members are called, some of these structural members are in tension, some are in compression, and some of them are not in any load at all at different times, depending on how the loading occurs. But this is just obviously, this is an older picture, maybe, I don't even know what, maybe it looks like the 50s or 60s, where there was a roadway that needed to go over train tracks. So anyway, there's some other great bridges more closer to home. I have a picture of it, but I couldn't find it today. But out south of town, there's a dam called the Willwood Dam, and there's a bridge. They used to actually drive over the dam. Now they've created a Warren Truss bridge going sort of, I guess it would be west, more or less west of the dam. So you go across that bridge, but it's a really neat one as well. If I get out there, I'll take a picture, but if you're going for a drive, it's really worth seeing. It's really a beautiful little bridge. Then there's other ones. One of my other favorite bridges is, and this is, let's see, this is in Newcastle, England. It's called the Millennium Eye Bridge, maybe, in Newcastle. Let's see if it will guess me soon enough. Yeah, here we go. And so this is like my thing. Whenever I go anywhere, I always look at the bridges. That's not all I look at, but I really love bridges. So anyway, what the Millennium Eye Bridge is this is a roadway, so you can drive over it, or this is a walking bridge only, I'm wrong. And then when ships come through, Newcastle is a big shipping port in northern England on the River Tyne, and you can see this bridge, this older arch bridge, is much higher in elevation. This actually rotates up when ships come through, so that let's see if I have a picture of it rotated. Here we go. So this is just the same bridge rotated. So the walking way rotates up. Of course, you don't want to walk across it at that point, and then the ships can come through. So then it rotates back down again. What's that?
I think that would be the most interesting time to walk on.
It is awesome. I have done it, and it's just beautiful. It's just absolutely beautiful. So I would recommend anytime you travel, go take a look at bridges. All right, last bridge, if I can find it. It's called the Lift Bridge at Houghton, Michigan. There we go. Okay, so this is the bridge I was telling you. It's called the Portage Lift Bridge, Portage Lake. And this is the big bridge between the upper tip of the Keweenaw Peninsula in the Upper Peninsula of Michigan. I never thought about that. It's a peninsula in a peninsula. Okay, so it's actually an island. Yes.
I just had one other bridge you should look at.
What is it?
It's the 3D printed Amsterdam Bridge.
Amsterdam Bridge?
Yeah, they 3D printed it while, at its position, they 3D printed it.
Okay, all right, let's take a look at that in just a minute. Great. Just to finish this, you see we have these humongous support spans, right? I mean, the supports, obviously designed to lift a lot of weight. This middle part of the bridge, which you drive across, except for when the ships come through, this lifts up so that it becomes taller so that the ships can go through. Interesting. All right, and then we're going to take a look at...
I think the best way to look is just Amsterdam 3D printed bridge.
Okay, let's find it. No, I'm not responsible for this content if Dane's pulling out. All right, so Amsterdam 3D printed bridge. There we go. Robots, complete span.
Yeah.
We want a picture, though.
Working on it last year.
Is this in Amsterdam?
Yeah.
Okay, I figured, but you never know. I was saying Amsterdam is I've never been there, but it's a pretty crazy place. That's right.
I don't know. I think there's
Isn't that crazy? So this is them drawing it? Yeah, let's go do that. Let's take a look. All right, let's find a...
It was crazy. They were just piling it well. Yeah.
It just wants to... It doesn't want to come back up again. I'm not... But now I want images. If you'll let me have images. All right, let's see. Oh,
Yeah.
there we go. Look at that. And there's robots making the bridge.
Yeah, they're 3D printing it.
Isn't that cool? Look at that. That's beautiful. Notice here we have, this is very beautiful, but it's still that arch. And we'll talk about why that arch is just a perennial design in bridge making. And then you'll see also this is a pseudo truss. It's not really a truss, but it's close enough. So basically these little feathery things are designed to take load in some pattern. Beautiful bridge, thank you. I'll add that to my pictures. All right, so now, where does this lead us? What are we doing and what are we talking about? Well, also on your Moodle page, we have a handout which talks about the analysis of plane trusses by the method of joints. So what we're basically doing here is we want to look at trusses, such as a Pratt truss, which I'm going to talk about Pratt's, Howe trusses, any sort of a structural member that's designed to bear and transfer load, and decide how much load is in each structural member. So if we were looking at the truss bridge, for example, I don't know if I can, there we go. Okay, this is my nice simple one. We want to know how much load is here. How much load is here? Is this in tension, compression? Is this in tension, compression? And what are the values? And this is the big leap from statics or physics, where when we would load a bridge in statics or physics, we just assumed that the bridge was going to take that load. But that's not really true, right? So if we have an ultimate load, if this is a 4-inch rectangular some sort of steel structural member, it has a limit. It has a load limit that cannot be exceeded. And it depends on the material, and it depends on the size of the material, and also on the shape of the material, and also to some extent the age and the number of times that this structural member has been loaded. So all of these things factor into the ultimate stress that the structural member is going to take. So as an engineer, when we design for anything, whether it's a horse trailer or a bridge, what is the magic about the ultimate load, whatever it is. You already know this, right? Do you want to go above it? Do you want to crowd that number? Do you want to design below it? Yeah, you want to design below it because you never want a bridge to fail. So it is typical, and we'll talk about this a little later on, that if we think this structural member could bear, let's say, 1,000 pounds, that we would design it, if we thought that, okay, let me rephrase that. If we thought that the most load that this structural member would ever take would be 1,000 pounds, we would want to build it with a structural member that would take 2,500 pounds. So we usually use, it's called a factor of safety of 2.5. We come up with everything we could think of, every reasonable thing that would increase the load on the structural member, and we multiply it by some number that's dictated by our profession. But generally 2.5 is a good number. And if you think about it, it makes sense because if loads are being transferred between all the structural members on this truss, if this one breaks, what's going to happen to the other structural members in the truss? Are they going to have, they're going to have more load, right? Yeah. So if they have more load, so in other words, if somebody didn't bolt this in properly, if the fasteners were not dealt with correctly, or if there was a flaw in our structural material, maybe it was cast improperly, or there's a weak spot or a narrow spot. If you have wood, you can have animals getting at it and making it less structurally strong than it should be, or that you're counting on, or you can just get a bad piece. You want to make sure that that's not going to cause a catastrophic failure of the entire thing. Yes?
So when you're doing this, do you calculate the actual weight of the material that is supporting itself?
Yes, actually you do. You add everything in. And we're going to just talk about a little piece of that today. Nobody gets to go home and design a bridge after our lecture today. But yes, that is the ultimate goal. So, and in machine parts, when things start moving, for those of you that want to be mechanical engineers, it's even worse because when things start moving, there's more opportunities to have failure on a bunch of different levels or to have extra loading on a bunch of different levels. All right, so going back over, beautiful robot bridge, beautiful Millennial Eye bridge, beautiful robot bridge, map of Michigan, beautiful Mackinac Bridge, Warren Truss. Here we go. This is on your Moodle page. So the analysis by methods of joints. Now what I'm going to do is you can follow along with this, and if you listen to my lecture while you are on your computer, you can pull this up and just work from it. But I'm going to flip over to the document cam and start writing some stuff down so that we have some ideas about what's going on here. She says she is. Let's see if it'll come up. There we go. Maybe. Yes. Excellent. Okay, there we are. So when we talk about the method of joints, what we are really talking about is analysis to determine load, and we're talking about tension or compression, and we're going to define all of these terms today in a structural member. So if I were to draw a simple little Warren truss like this, all right? Every time that I have the actual physical metal or whatever this is designed from, toothpicks or wood or plastic or whatever, these are referred to as structural members. And anywhere that structural members come together is referred to as a joint. So if I call this joint A and this joint B, I would call this structural member AB. Right? Now that is just convention. If you don't do it that way, you're not going to die. But what would this structural member be then, right here? Would this be structural member BC? And if this was D, what would this one be up on top? I think Eddie knows. Thank you. Very good. This is structural member BD and so forth. This would be CD. And if this was E, this would be DE. And this would be CE. Okay? So we have trusses are composed of structural members and intersections of joints. Now, generally speaking, when we have a truss like this, or any sort of, it doesn't have to be a truss. A truss is a particular kind of a structure, and I apologize in advance. I sometimes use those two terms interchangeably. A truss is something that bears load that has a design based on a triangle or a three-sided shape. And there's a reason for that we'll learn in just a minute. But any sort of a structural member, if I say truss, structural member, I'm using truss in a very loose and probably not totally accurate fashion. It is accurate, it is true, but maybe it's not as precise as it should be. Okay, usually bridges or other structural or other structures are supported externally. And generally speaking, because this is, if you have something that's like loaded with cars or any sort of a load, like these roof trusses are sort of the same thing, where you have a dynamic load. Sometimes the wind blows, sometimes there's snow on the roof, sometimes you have animals walking up there if you live in the country, whatever. So the load varies a little bit, but generally there will be some sort of an external support. But if it's loaded very heavily, depending on the characteristics of this material, it can lengthen a little bit, and then when the load is removed, it can contract a little bit. So we generally have one fixed support, one or more fixed supports, and then we have at least one rolling support, so that when this expansion and contraction occurs, that it won't make the bridge buckle or pull apart in any way. Now, a really easy example of this, or something that you've probably seen that goes along with this, is if you ever have laid a sidewalk or looked at a sidewalk, walked down a street, generally speaking, the concrete of the sidewalk, or even if it's bricks or whatever, there's always these little gaps in between, and those are called expansion joints. If the expansion joints aren't present, what can happen to the sidewalk over a very cold winter or a very hot summer? Yeah, it buckles up. Yeah, and so you get these like whoop-de-doos when you're walking down the streets in Powell. Some of them are like that, I know. So the expansion joint just occurs for the change in length that occurs due to mostly weather when you're talking about sidewalks, but roads and bridges and so forth, there's lots of reasons that we have expansion and contraction. We have a change in size. All right, so now the other thing we've talked about is tension and compression. Both of these are types of what are called normal forces. And I'm putting it in quotes right now just because I want to define it. Normal stress. Okay? When I say normal, I do not mean as opposed to abnormal. Normal just refers to something of a perpendicular nature. So as we get into this course, we're going to learn that we look at bearing normal stress, which is either pulling or pushing. In other words, it's perpendicular to the cross-section of the member. The other one, if it's parallel to the cross-section of the member, is, I said that wrong. Let me think about this for a second. Parallel. If it slides the member this way, let me just draw a picture. If you have a cross-section, this is a pipe or something, or a structural member, for example, and we pull on it, this is the cross-section. So what we're talking about in terms of that normal relationship is that this load is perpendicular to the cross-section. And that is referred to as a normal stress. And if it's pulling, that's referred to as tension. If we have something that's being pushed upon, once again, that is still a normal stress, but it's compression, and it's also a normal stress. So this is what we're going to talk about today. Later, we're going to talk about something called shearing stress. And shearing stress occurs where the angular relationship is a little bit different. If I have a structural member, push on it this way, push on it this way, and it tends to deform it angularly instead of pulling it apart or compressing it. All right, so today we're going to talk about tension or compression. So the end game for us is we would like to know, based on a certain load, whatever our load is, what the tension or compression is in each one of these structural members, and based on this external loading. So we're going to go back to some basics. We know that if a structure is not moving, that the summation of forces in all vector directions has to equal 0. If they do not equal 0, this comes from Newton's second law of motion, summation of forces in any vector direction is equal to mass times acceleration. Now, what I'm really saying is acceleration is equal to 0, so it could be moving at a constant velocity, but when we're talking about structures, that is not applicable. But basically, mass is never equal to 0 for any real structure. So if the summation of forces in a particular vector direction is not equal to 0, that means that our structure is going to be accelerating or pulling apart or blowing off the skids or whatever. So, so we can start with this. For any structurally stable element, this is a requirement. Okay? But it turns out, if you think that there's even more to this story, if you look at my structural, my structure, if you think about it, if I have a load based on the weight of the structure here and a load based on the weight of the structure here, I'm going to have responsive loads at those external supports. And if I have some other loads, I have some cars going across it or whatever, that everything has to sum to 0 on the entire structure. But this may not be as apparent, but if we take just a piece of the structure, like if we look at this joint, let's just look at this joint since we're going to talk about methods of joints. The summation of forces going into that joint also have to be equal to 0. Because what would happen if it wasn't? If we had more load here and this was just pushing really hard on joint A, what would happen? It would break. That is exactly correct. And if it breaks, we no longer have a structure. So by virtue of the fact that it's not breaking, we can guarantee that the forces going into this vectorially added together have to equal 0. In other words, if the structure remains intact, the summation of forces going into all joints in the vector sense, I'm just talking about A here, but all of them, has to equal 0. So if I look at an analysis of the joint at A, I can say that the summation of forces in the y direction going into joint A have to be equal to 0, and the summation of forces in the x direction at A also have to equal 0. Now, we don't have to choose x and y, but we always choose orthogonal coordinates because then we don't have to get into the whole law of cosines thing. We can just sum things in the x direction, sum things in the y. There are times where you might reorient your grid to some x prime, y prime, but as long as you keep things, or what else, radial coordinates or any of those other things that they taught you in math that kind of make your head swim. But you can do normal tangential, you can do radial, but in this class we are going to do exclusively x, y coordinates. Okay, we'll talk a little bit about orienting differently about 12 weeks from now. But for now, x and y will take care of us. All right? So what that means is that if I look only at joint A, I have a structural member AB coming into joint A. I have an external reactive force at A, and I have some sort of a structural member AC that is either in tension or compression. And I have 3 forces, and they have to sum to 0 in the x direction and the y direction. The next piece is that because they are normal forces, and this is another thing that may or may not be apparent, the force has to be directed, the force in AB has to be directed along AB. The force in AC has to be directed along AC Just, it has to, because that's what the structural element does, is it bears a force along its length. Okay? If it didn't, so what that means is that the angular relationship of the truss is also the angular relationship of the forces. So when we do a free body diagram of the forces going into A, we can use the angles of the truss itself to show us what the angles will be going in and going out. All right, and that they have to sum to A, or they have to sum to 0 at A. So I'm going to work several problems for you, or at least, let's see, it's 10:40. I'm going to work some kind of a problem for you before we leave today. And if not, we'll leave off there and we'll start again on Monday. So the other part of this is, how do you determine if a structural member is in tension or compression? Well, the answer is, you ask yourself the question, is the structural member pulling on the joint? And if it's pulling on the joint, that means it's in tension. Or is the structural member pushing on the joint? And if it's pushing on the joint, that is compression. So on your handout, I'm just going to see if they illuminate this. I'm going to come back over here to the podium PC. Okay. Here is a diagram and two little free body diagrams that I'm going to teach you. I'm going to teach you how to do this. We have, what this is saying is, on this little Warren truss, we have an upward force of 5 kips. I don't know if you remember, kip is kilopound or 1,000 pounds. 10 kips here being pulled down, so we have some sort of a load at joint B, and then we have another reactive force at C. So since we're not going to get finished today, I'm just going to go through this a little bit. First of all, you'll see if I were to do a summation of forces on this truss, it would equal 0, because I have 10 kips pushing upward in the y direction, 10 kips pushing downward in the y direction, and nothing in the x direction. So summation of forces x on the entire structure is equal to 0. In the y direction, summation of forces on the entire structure is equal to 0 in the x direction, because there aren't any. All right, now if we take a look at this joint, I'm just going to draw their joint A, and I'm going to use their numbers because I think maybe that will illuminate this a little bit. So I'm just going to reproduce this. Here's joint A. We're told that we have a reactive force here of 5 kips externally. And then, oops, let me come back here to the next page, just because joint A is up a little bit. Okay, now here's the deal. We have AD right here, and we have AB right here. And we don't know what direction they're in, do we? We don't know if this is down. We don't know if this is over. But we can make a pretty good guess, and in this case we can be certain. 5 kips is pushing up, right? So AB does not have a y component because it's purely horizontal. AD has a horizontal and a vertical component because it's at an angle. So in other words, in order to attain this requirement of summation of forces of y equals 0, if this is pushing up, AD has to be pushing down, doesn't it? Do you see that? Because it's the only thing that's going to counteract that 5. So it has to look like this. All right? Then what about AB? Well, there's no horizontal component here. AD is the only one that has a horizontal component. So if this is pushing to the left, or the negative x direction, what does this have to be? To the right, correct? So it looks like that. All right, now we're going to leave off in just a moment here, but I want to describe what this means. AD is pushing on the joint. AD is pushing on the joint. And that means it has to be in compression. Therefore, AD is in compression. Okay? What about AB? AB, if you look at the arrow, just think about putting your hand on the arrow. If it was an actual arrow, you're pulling on the joint, right? So what about AB? AB is pulling on the joint. Therefore, AB is in tension. All right. So at this point, we've done some preliminary work to get ready. We don't have anything that we can do homework on yet, but there is homework at the end of this handout. I will, at some point, give you the problems that you will need to do for homework, but it looks like you guys are off the hook for the weekend. Do you have any questions about this? Do you understand what tension and compression looks like? Do you understand why this one is in tension and this one, or this one is in tension, this one is in compression? Does it make sense? All you have to do is think about the joint. You don't think about the structural member. Think about the joint and think about whether the structural member is pulling on that joint or whether it's pushing on the joint. So if it's going into the joint, it's compression. If it's coming out of the joint, it's tension. All right? All right, ladies and gentlemen, that's it for today. So I will go ahead and turn off my streaming. We'll leave here, and then we will take this up on Monday morning for more fun with tension and compression methods of joints.